Okay, I think we're good to start. Hi, everyone. Thanks very much for coming to my talk, Evolving Systems Design with Linkerd. My name's Ed. I work at Form3. I'm a developer there. And we've done a really interesting thing over the last 18 months. We've integrated our platform with all of the important payments infrastructure in Europe. So we started off with doing that with Faster Payments, which is a real-time payments platform in the UK. Then we did batch-based with Bax. And we've recently done SEPA Instant in Europe, as well as Swift. And we've had to deal with a lot of legacy technology, some of them dating back from 1968. So that's been a lot of fun. So we've dealt with everything from flat files with fixed width message formats, all the way up to cutting-edge 1990s SOAP XML technology. And the reason that we've done all of that painful integration is so that our customers don't have to. So they can rock up to our JSON API with web callbacks and cloud-based queue callbacks, do one straightforward integration, which takes roughly 2 weeks, and they can achieve as much as we did in the last 18 months. So that's the kind of business concept behind this, is that our customers are usually financially regulated institutions which want to send and receive payments from other bank accounts. So that's the nature of the business. It's quite an exciting business idea, and it's proving very popular, and we've got a lot of demand from banks. So back to sort of the topic of this talk. I really like stories about software and hardware development, and I've highlighted two of my personal favorites here. Dealers of Lightning, which is about the story of setting up a research laboratory in Xerox PARC. Xerox decided in 1970 that they needed to understand what the office of the future was going to look like, because they were a photocopying company and were worried that they wouldn't be relevant in the future. So I think that was quite a cool idea, and they got some really brilliant scientists together. And the scientists made a very shrewd observation. They thought that they would set up their research center as far away from head office as physically possible, so get away from all of the managers and concentrate on building the office of the future. It was very interesting. In 3 to 5 years, they developed amazing technology. They started off with the laser printer, just to keep the folks back in New Jersey happy. Then they developed Ethernet networking, which kind of makes sense. You could then network your computer. They then went on to invent Smalltalk and object-oriented programming and bitmap graphics, and the first personal computer that had a graphical user interface, which I've got a picture of here. It's the Alto Star. And they did that all within 5 years, which is pretty amazing when it took us 18 months to integrate a payment system. I'm impressed with that. Another book, which I really enjoyed reading some years ago, was about the race to invent the next generation operating system around the Windows 3.1 era. Microsoft realized that their architecture wasn't going to cut it. They embarked on a joint project with IBM with OS2 Warp, but secretly, they also set up another project to develop the Windows NT kernel, and they poached Dave Cutler, a computer scientist from Digital, who I think was the lead engineer on VMS. And this book goes into some of the technical nitty-gritty that his team went through, as well as some of the interesting politics in Microsoft to get that shipped. It's a really fantastic book. So my story is nowhere near as exciting or interesting as that, I'm afraid. But it's all about day-to-day software development in small teams. And I've worked with the same engineering team across 2 different systems. And I want to show you we had problems with reliability of service-to-service communication on both of those systems, and some of the techniques that we used to make that more reliable. So in System 1, we increased the reliability, and we reduced some of the latency. Did a similar thing in System 2, which is the current platform at Form3, but we added circuit breaker technology to protect services under stress. But we still got quite a bit more work to do with tail latency. So what is tail latency? If you lined up all your requests from fastest to slowest, you quite often see that you get this hockey stick at the end of the last 1 percentile. So you can see it here. Whoops, sorry, a bit shaky hands there. And you might think, well, that's not really a problem because it's only 1%. But if you've got 1 million users that are making one request to your API, that means that 100 users are going to see the worst part of that tail latency right at the top. And 10,000 of your users are going to see some part of that tail latency. So it does turn out to be quite a big problem. And that's amplified if your page view has several calls to your backend. So if you've got 10 requests going to your backend, that's no longer 10,000 users, it's many more. So this first system that we worked on was a trading application. You could buy and sell shares, commodities, and FX. You've probably seen one of these systems before. It was the monolith. It was the worst kind of monolith, the dreaded distributed monolith, where we had all of the trappings of SOA architecture, but we had all the disadvantages of a single shared database and data model. So it's quite hard to work on this system, but nonetheless, we endeavored. The basic design of this system is you've got requests coming into the load balancer, being sent to the API gateway, then popped on a message broker request queue, then being dequeued by one of the service instances, putting back on the request response queue, and being sent back to the user. And this design worked really well under normal conditions, but it didn't always work. And sometimes we got reports from customers that they would do stuff on their UI, but nothing would happen. And it's because we were getting timeouts somewhere in this message broker architecture. So we talked around and asked people, what was the purpose of this message broker? Because we couldn't see in the code that it was really doing anything useful. And no one really seemed to know why it was there. So that was a shame. So we decided to remove it in the lab, and we just put a straightforward HTTP load balancer in between. And it worked a whole ton better. We're getting much lower latencies, and we thought, well, we've solved this problem. Aren't we clever engineers? So we sort of high-fived each other, went to the pub, problem solved. Unfortunately, about a week later, we started getting these timeouts again. So that was a bit annoying. So we reopened the project, and we noticed that there were very rare events that would cause these timeouts. So they were a lot less frequent now that we got our load balance, straight-through load balancer. But it was 1 in a million or something would time out. And we noticed that these correlated sometimes with garbage collection events in the processes, or sometimes strange network activity on the network card. It would just get saturated. So we came up with a theory that if we had just retried, the next request would have succeeded because it was just a very rare event. So we introduced this library in our API gateway, which we very imaginatively called the retry library. And it basically just retried the request on one of those rare events. And that approach worked very well. So we rolled that out to production thinking, we've definitely solved it this time. And lo and behold, we'd actually broken the system quite badly on very busy days because our retry logic didn't have any backoff built into it. So if a service was really struggling, it now got absolutely hammered by our retry library. So we then started to learn about circuit breakers and why they were a good thing, which sort of now brings us on to the second system, was Form3. And we learned a few lessons about circuit breakers, and we wanted to carry those forward into this new system. And we thought, well, there's no sense us writing more retry libraries. Surely, other people who are better than us at engineering have solved this problem and spent a lot more time on it. And so we started looking in the open source community to see solutions out there, and we found Finagle from Twitter, and they had spent a lot of time doing exactly what we wanted to do. There's a slight problem, though, is it was tied to the JVM, which was something that we weren't interested in. So we started looking further afield and came across Linkerd. And they had taken the Finagle library, essentially taken it out of process, and they're now inside the request flow as a proxy. And they've added features on top of Finagle, but they've got that core Finagle inside it. So you get all the good client-side features like timeouts, retries on failures and timeouts, They've implemented that important circuit breaker pattern for us. It's got a really good way to do security using TLS. It's just quite straightforward. And it's got the ability to very easily integrate with common service discovery tools. It can do different types of deployments, integrates with distributed tracing. And here I've got a distributed trace for you that is an example from our early prototype of one of our core payments APIs. It's quite hard to see on this slide, but essentially this call stack will enable you to look at what microservices are calling what microservices. And at the top here, you can see that we're calling the payment API, but that is in turn calling the user API to check that you're allowed to carry out that function. But for some reason, the user API is then calling a whole bunch of other services, and we hadn't realized that until we started looking at these tracing graphs. And that led us to redesign this payments API system so that we were using JWT tokens to sort of distribute permissioning around the system, and then we didn't need to call the user service quite so often. So these sort of tracing graphs were very, sort of critical in our early development cycles, and we still use them regularly to debug production issues. So we decided to deploy Linkerd in its most common deployment model, which is called linker to linker, where each node in your system has a local Linkerd daemon, and you proxy all your service-to-service communication through Linkerd. We also proxy outbound traffic to third parties through Linkerd as well, so that we get visibility on calling third parties. And you might think, well, this kind of looks like a bit of an overkill. Why would I want to do this? Well, you get all of those client-side benefits, which we talked about earlier, the retries, and you also get the ability to have all your traffic encrypted, and you only need to worry about managing encryption in one component of your system for sort of on-the-wire encryption. So you don't need to worry about how do you do TLS in Java 1.8, how do you do it in Golang, how do you do it in .NET. We just encrypt it using Linkerd, and the other services don't need to worry about that concern. And the management of those certificates is simplified because we know that they're only in Linkerd, so that we obviously don't let them expire. Another benefit that we sort of fell into, really, was that we then noticed that the only communication between nodes was going via Linkerd, so we locked down the security groups on our EC2 instances so that we only allowed Linkerd traffic to talk to each other, which sort of narrowed the attack surface and allowed us to sort of prioritize patches to Linkerd or JVM-related patches, which was useful. Okay, so I've got two little demos for you today. The first demo sort of represents system one before we started work on it. And I wanted to show you what that looks like to the end user. So I created 10 virtual users using a little tool called K6, which I came across whilst preparing this demo. And it's a very easy way to do some load testing. And it publishes its metrics to Influx, and we can then look at them in Grafana. And it's just going to send those requests to a load balancer, which distributes it to these services. And I've got 4 instances of the same service. 2 are super healthy, which are these, if I can do this, which is that one and that one at the bottom. And then one has got this delay sickness. It's a mild case of delay sickness. Only 2% of traffic will get delayed by about 1 second. And then the third instance has got a terrible bout of 503 sickness. And has been hospitalized. So 40% of that traffic is going to return a 503. So I'll just start up this demo, and then we'll have a little look at the Docker Compose file. All in Docker Compose, but I don't know if anyone else has solved this problem, but the sort of getting all the timing right, I had to use some little bash scripts that I put in the bootstrapping of this. It seemed a bit awkward, but it's the only way I could get it to work properly. So you can see there that it's kind of sleeping, waiting for that load balancer to come up. Thankfully, it has come up, so now the load testing tool is going to kick off those requests. So I thought it might be worth just quickly taking a look at some of the Docker files here. So at the top, I've got this traffic simulator. Using K6, it was very easy to create 10 virtual users and have this little JavaScript file run for 5 minutes. And this JavaScript file is dead simple. It just hits the load balancer endpoint. And by default, K6 publishes a lot of interesting metrics to Influx, but bizarrely didn't publish the HTTP status code. So I hacked together a little statement there to add some buckets. So we've now got it hitting the load balancer, which, as I mentioned, is an Nginx configuration. And it's really straightforward. It's just listening on port 80 there, and then it's proxying everything to this upstream label, system 1. And here we've got those 4 services defined there. So it's going to round robin each of those services. And here you can see that I wrote a little echo program, and if you, it just echoes out this text, but then you can give it these sicknesses like delay or response code. And then the rest of this file has just got the infrastructure. Now, my Mac might start to levitate as all the fans spin up, because this is quite intensive stuff. But we can now go and look at the result of this and you can see that we've got quite a lot of error codes coming here, roughly about 10%. And we've got these outliers that have delayed for about 1 second. So, that was sort of an exaggerated view of that first system before we started working on it. If I quickly go back to, now just in case I hadn't gone to the demo gods altar frequently enough over the weekend, I had some canned screenshots that show the results of that demo. So the second demo is very similar, but we will inject Linkerd into the request flow. I should note that you could remove Nginx here, but just because I was lazy, I didn't want to change this load testing script, so I just kept it in there. And so that Linkerd knows where those services are, I decided to use console, which was dead easy to set up for Linkerd. So we'll just stop that demo and start the next one. I need some sort of intermission music or something to keep this going, but I just want to check. This has never failed in the 10 times that I've practiced it, but you never know. Yeah, there we go. So it's come up. So the second Docker Compose file is very similar. We've got all the same components, but we've added a few new ones. So we've got the Linkerd container here, which is very simple to set up. All you need to do is mount a volume that's got your configuration file on it. And we're worth looking at that very quickly. This is sort of what's required to get console integration. You just add this namer here. And then we've created one simple router, and we've given it some sort of characteristics. It's allowed to retry failed requests. And this %can retry basically means for every successful request, you can retry twice for failure. And then we've given it some very aggressive timeouts, which are not really production kind of timeouts. It was just to demonstrate the demo of how Linkerd will kick in on a timed out request and retry it. And the reason that Linkerd is able to find our services is we've got this D tab here, which took me a while to get my head around D tab. It's sort of a bit like regex. You learn it, then you forget it, then you learn it again. So yeah, essentially what it does here is it uses this identifier and says that the first segment of the URI, so after the host, it's like /service1. It will then pipe that to console and ask for service1 instances. So I can show you that here. I've got console running. If we just go back and refresh that, it's going to pass service1 to Linkerd. Linkerd is going to hand that to console, and console is going to come back with these 4 nodes, and it's going to send it the IP address and port numbers there. And we had to update Nginx, make it a bit simpler, so instead of proxying to its upstream label, it just forwards all the traffic to Linkerd, and that's that path segment that I was talking about that's used in the lookup. So those DTABs can be a little bit more complicated. This is probably the simplest DTAB you'll ever see. So yeah, the only other thing I needed to do was somehow register the services with console as they spun up. So an easy technique to do this is to use console registrator, which is a little Docker container that hooks into the Docker socket and listens for containers spinning up. And anything that's got an exposed port, it will register in console for you. So it's very useful for this sort of demonstration stuff. We also use it in our production platform as well. And then I added the infrastructure components. So hopefully, whilst I've been speaking, this has been going nicely in the background. And if we go back to our Grafana status codes, you should see that we've had a lot less errors during demo 2, in fact none. And we've also pulled in some of those outliers. They're now sort of hovering, I mean they're still infrequently, but they're hovering around 200 milliseconds. I'll just show you the homepage of Grafana because the K6 guys have done a nice job of sending some metrics with their load balancing, their load testing tool. So you can see here a few more things of the percentiles for those durations. So just to show that it's not all smoke and mirrors, I think it's interesting to look at the Linkerd dashboard. This is what each node of Linkerd has its own dashboard, and you can see real-time statistics. So you can see here at the top we've got the router, and it's got 100% success. But you can see down here that this retry budget is flickering. That's because failures are occurring in the network, but it's retrying them. And then you get a breakdown per service, and you can see here retries and failures occurring regularly as we go along. But the end user isn't getting any of those errors back. And because we plugged into Zipkin, we can go and look at some of the tracing. So this was a happy path trace. So the outer span is the ingress into Linkerd. So that's our request going into Linkerd on 4140. Then Linkerd is calling our service, service 1. That's that span. And it's taking 7 milliseconds to process that GET request. Then the last span, I just wanted to demonstrate how, as a developer, you can send your own telemetry to Zipkin. So in my little Go program, I've sent it a span that said that this data access took 12 microseconds. But if we look at, let's try and find some more interesting ones. So maybe this one. That's okay. So this one's an example of a retry. So here you can understand why Linkerd was retrying. So if we click on this span here, you can see that it got a 503 back from the service. So that's why it did the retry. And if you hover over there, you can see the annotation. And I think it got that twice before the last one was successful. We can also look up super slow requests in Zipkin and take a look at those. So here's one that took a second. But what's interesting about this one is, although that span here took a second, you can see that the user got a reply in 200 milliseconds. That's because Linkerd, if we click here, it timed out that request that was taking a long time, and you can see the information in here that's saying it's timed out, and then it's retried it. Okay, so that is the end of that demo. So here are the sort of results of those two demos side by side. And I think it's obvious to see the error rates have dropped, and those outliers have changed. That y-axis is different. Instead of a second, it's 200 milliseconds. So I recently read a paper that Google published about the tail at scale. So this is an approach that Google have taken at further reducing those outliers, because you can't really just use timeouts. That doesn't really work by lowering the timeouts super low. In production, that's not really feasible for various different reasons. So Google's approach to this was to use a technique that they've called hedge requests, which is essentially they're betting on the fact that there's a small chance the request is going to go wrong. So rather than take the hit of retrying that timed out request and the end user getting a bad experience, they will hedge that and send multiple requests all at the same time. And that paper takes you through in quite a lot of detail their approach to that. So I'm not sure if that's an avenue that we're going to go down in the future, or if the community is going to go down that avenue with service meshes, but it'd be interesting to see if that's an approach that we can use. So here you can see that the third service was the first chat to respond, and then the other two got a cancellation message to say don't bother processing. So yeah, to wrap it all up, we've really enjoyed using Linkerd, and we've seen that it's been an easy way to implement the retry and circuit breaker patterns, and to manage TLS, and definitely very helpful with the distributed tracing. So I just wanted to say thanks very much to the Linkerd community and its maintainers. They've been super helpful whenever we've had problems. They're always there on Slack. It's a very welcoming place. So thanks very much to those guys. This demo is sort of party bag wrapped. You can take it home with you. If you want to clone that repo, you can just try it out at home. And yeah, finally to mention that we're a young startup, small team, and we're looking to grow. We're looking to hire engineers remotely or working in our London office. We're looking for people that are interested in open source, sort of cloud native programming and software, as well as people that think that payments is something that might be able to interest them during their day job. So yeah, thank you very much. So any questions? Yeah.
In those examples you showed, like you have a single instance of Linkerd running, and what would be the benefit of having this separate instance in each of the services?
Do you mean like a sidecar deployment?
Yeah.
I think I'm not a super expert on these deployment models, but as I understand it, if you have the benefit of the sidecar approach, is that if the Linkerd node died, your other services would still be alive. But in our deployment model, the per host deployment, if Linkerd dies, you need to consider that whole host as dead. The sort of disadvantage of the sidecar, I suppose, is that at the moment Linkerd is based on the JVM, so it has quite a high memory footprint. So you'd need to bear that in mind, I suppose. Yeah.
So what's the extra cost in CPU that you've seen when you run those DVDs?
We did measure it early on in the project, the extra overhead of using Linkerd, and for our sort of scenario, our latency kind of requirements, it was negligible. It's also the communication happens locally on the node, so it's not an extra network hop over a wire, it's an extra local loopback hop. So we decided that for the benefits that it gave us, that was a trade-off that we were happy to make. Yep.
So now you did the service discovery with console, and I assume that you can just throw out the whole console thing, and then Linkerd talks to Kubernetes to do the service discovery.
So it was your question, it could talk to any service discovery? Or?
Yes. So
yeah.
you can essentially
Yeah, so that's right. Yeah, console was used for this demonstration, just as it was an easy route to get it up and running. But yeah, you could plug into any service discovery. I've forgotten the list of ones that it supports, but it's quite a long list, if memory serves. We use console on our production platform. That's why I'm sort of comfortable using it. But yeah, I guess that's another good thing about Linkerd is it sort of plays nicely with lots of other tools.
What do you see in Kubernetes that's relevant to your business right now? What's emerging that can help you?
Yeah, it's a good question. At the moment, we're not running on Kubernetes. When we built the platform at the time, we didn't know much about Kubernetes, and we're quite a small engineering team, so we went what we were comfortable with, and we didn't have a lot of time to spend on sort of Docker orchestration. So we're running on ECS at the moment, and I think that's definitely something that we want to look into in the near future, is going to a better orchestrator. So sorry, I can't answer that question any more than that. Sure. Hi.
How do you think service mesh replaces a distributed tracing system? And if it doesn't replace, how they work together?
Yeah, so I think the question is how does a service mesh replace a distributed system, or if it doesn't? Sorry, distributed tracing system. Yeah. So I mean, in my experience, they sort of go hand in hand. So we're using open tracing and Zipkin, and we use it integrated into Linkerd, and we also send trace telemetry outside of Linkerd. So they sort of work together quite nicely. Oh.
I'm not an expert in the Linkerd story, but I really like the idea. Would the Linkerd replace the engine systems basically for the load balancing?
Yeah, so that's right. And I probably should have done that, and it's my bad. Removed Nginx from the second demo, because Linkerd has got its own load balancer with several different algorithms that you can choose from. And I'm not qualified to speak on all of those algorithms, but I know that the default one is fairly sensible. But they tend to be much more intelligent than your traditional hardware load balancers, because they have a lot more data about how services are performing and which network routes are the quickest, because they're in the flow of the traffic and they're analyzing the response times. So yeah, we don't use load balancers in production sort of at that part of the infrastructure. We only use them right at the top, at the ingress from the sort of the public routes in. Oh, sorry, yeah.
What kind of traffic can it load balance? I mean, if you have TCP or HTTP or
Yeah, so it only can load balance, as far as I'm aware, HTTP traffic. They have another project that I'm not familiar with called Linkerd TCP, which I think is now superseded by Conduit, which does TCP load balancing. But you want to talk to the Linkerd guys at the booth about that. They're the experts. Sorry over here. So would it be okay to use that microphone? I can't hear you too well. Sorry.
So my question was if you know if Linkerd has any feature for sticky session or session affinity, so layer 7 load balancing based on some key.
Oh right, that's a great question. I've no idea. I'm sorry. No, we don't have that scenario to worry about in our infrastructure, so it's not something we've come across. Sorry.
I see, thank you.
I think there's a question over here. Yeah.
do you plan to use the routing of Linkerd for the canary release technique, for instance, when you put new things on production?
Yeah, so the question is, do we plan to use the Linkerd routing to do canary releases? We really want to look at our deployment model sort of holistically. So at the moment, that's one of the things. It's a big project that we want to kick off, is how do we do deployments, canary deployments. I think that's definitely an option, isn't it? As I've seen, it's a feature. It's not one that we use at the moment. But But I think that's I'm hoping to talk to people at this conference and get a view on the different ways that we can do deployments. We haven't solved that one yet. So I'd hear first and then I'll get back to you. Yes? Sorry, can you use the microphone? I'm really struggling to hear.
Yes. Do you know how you can configure Linkerd to handle post requests? For example, you have a request and just want one single request to be executed, like you're doing a reservation.
Yeah, so Linked's got the option on the retries to say only retry like GET requests, or you can configure it to also retry like post, patch, put, delete requests. So depending on how idempotent your backend is, you can configure it either way. So we use request IDs in our system to make all requests idempotent, so we can retry any of them. But I guess everyone's situation might differ on that. Thanks. So, yeah.
You mentioned before about pauses due to garbage collection in your app affecting response times to clients.
Yeah.
Given that Linkerd is running in the JVM, I was wondering if that affected you at all.
Yeah, that's a good question. We've not seen that, but I guess it must be an option as it's running on the JVM. So that's a good question.
Maybe using native memory management. It is, probably. Like the Java guys that does networking, they don't trust JVM.
So yeah, so I do apologise. I'm not a Linkerd expert, so I'm struggling with some of these questions. But that's an interesting one. Okay. Here first, yeah. So we have a request ID, and if the back end has already seen that request ID, it will throw it away. But if it hasn't seen it, it will then process it. So it's quite a simple technique to know if we've processed the request or not. So if it's lost in between the client sending and the service receiving, it will be safe to do the retry. Yeah, so the ID is sort of stored forever with the resource that you're creating. So maybe one last question, we better wrap it up.
Can you log somehow the responses from the backend that you are retrying so we can debug?
Yeah, I've not found how to do that. That's something I've often wondered is how, because the information that you get in Zipkin is just the status code. You can't see the request. So we've had to fall back to other mechanisms for logging that at a different place in the sort of the infrastructure. But we do have a way of like logging, dumping the whole thing, but I've not found a way to do that with Linkerd. All right, thanks a lot, guys. Cheers.